Okay, in this video we will explain systems of two qubits. Remember that our interpretation for a qubit is given by two disks, and if we label this disk 0 and this disk 1, then we have a state when we draw a segment from the center, starting from the center of length R1, and another segment starting from the center of length R2, with the condition that R1 squared plus R2 squared equal 1. This is a possible state for one qubit. And let's suppose that we have another qubit. And let's draw this qubit like this. We have 0, 1. And let's suppose that we have some R1 and some here R2. The condition here is R1 squared plus R2 squared is equal to 1. Then this qubit can be represented in this way. We have a complex number times 0 plus another complex number times 1. Notice that we can be more precise. If this angle here is phi sub 1, then C1 is just R1 e to the I times phi sub 1, and same thing for C2 would be R2 e to the I phi 2. Okay, same thing here. We have this state can be written like a W1 0 plus a W2 1. Then how do we represent this state made by the two qubits? Then we can do like the distributive property, and then we will have C1 W1 this times this, and then plus C1 W2 this times that, plus C2 W1 1 and 0 plus C2 W2 1 and 1. And this works perfect, but the problem is that in order to differentiate what information comes from this qubit and what information comes from this qubit, we will need to use two colors, and we don't want to do that. Then one way to avoid using two colors, we can label this, let's say, if we label this qubit 1 and this one qubit 2, then we can have the rule that we are always going to do the qubit 1 on the left and the qubit 2 on the right. That means that we will rewrite this like C1 W1, let me just write C1 W2, C2 W1, and C2 W2, but we're going to write the qubit, this one on the, the qubit 1 on the right, then the qubit 1 on the right, and the qubit 2 on the left. Here is 1, and here is 0, and here is 1. Then we're going to denote this qubit, and we're going to, since we know the order now and we know where the information comes from, then we're going to write this like this: C1 W1 0 0 plus C1 W2 1 0 plus C2 W1 0 1 plus C2 W2 1 1. We can go further and organize this information better. We notice that essentially we have 4 complex numbers, right? 1, 2, 3, 4. But how to organize these 4 complex numbers? And let me write down, we have 4 complex numbers. Which number should be first and which should be second? Then we use binary numbers. Remember that in binary numbers we have that 0 can be written as 0, 1 is just 1, 2 is this binary number, and 3 is this binary number, but I can write 0 like 0, 0, 1 as 0, 1, 2 as 1, 0, and 3 as 1, 1. This is just how to write using binary numbers. But then we're going to call this, we're going to call the first complex number. This number is going to be the first complex number, which is the second complex number. The second complex number will be 0, 1. This will be the second. And this will be the third. And this will be the fourth. But that means that this state, given by having this state in this qubit and that state in that qubit, can be written as a ordered 4 complex number. And we have here C1, W1, second is C2, W1, C1, W2, and C2, W2. That means that this state can be viewed as, naturally viewed as an element in C4, right? Let's have an example of this. Let's suppose that we have this qubit, let's say 1 over the square root of 2, 0, plus I times 1 over the square root of 2, 1. This is qubit 1. And let's suppose that we have here 1/2 I 0 plus a square root of 3 over 2, 1. Then our 4 complex numbers are going to be, we know that this is going to come on the left. Then we have for 0, 0, we have the first number is going to be 1 over 2, a square root of 2, and let's call this 0, 0. This 0 is because of this, and this 0 is because of this. And then plus, let's do this. This would be, I'm doing this times this. Now, this times this. This is, I think I'm forgetting the I here. And then here we have a square root of 3 over 2, a square root of 2. We're writing this one on the left and this one on the right. This is qubit 1 and then qubit 2. And then plus I times I is -1. Will be minus 1 over 2, a square root of 2. We're writing this one on the right and this one on the left. And then, and I'm forgetting, no, I'm not forgetting the I. And now we do this times this, which is plus I times a square root of 3 over 2, a square root of 2. And we're writing this one on the right and this one on the left. Then our complex number would be, this is the first number, I over 2, a square root of 2, and which one is the second? This is the second, minus 1 over 2, a square root of 2. This is the third one, a square root of 3 over 2, a square root of 2. And the last one is I, square root of 3 over 2 square root of 2. Okay, then this is the representation of the system when we have this state on qubit 1 and this state on qubit 2. It's given by 4 complex numbers. Something that we can check is that, let's call this complex number, how should I call it, U1, U2, U3, U4. We can check that U1 times the conjugate, that means the length of this complex number square, plus U2 conjugate plus U3 times U3 conjugate plus U4 times U4 conjugate. Let's see what is this. This would be 1 over 4 times 2 is 8, plus this is 1/8, plus this one would be 3 over 8, and this one would be also 3 over 8, and this is equal to 1. This is not a coincidence. Actually, we can prove that in general, under these conditions, if we call this vector U1, U2, U3, and U4, then we have the same property. Because if we start with a qubit here and a qubit there, then we have this. Then we may wonder, okay, can we reach every possible vector that looks like this, U1, U2, U3, and U4, with the property that U1, the norm of U1 is square, plus the norm of U2 is square, plus the norm of U3 is square, plus the norm of U4 is square, equal to 1. But can we reach every combination U1, U2, U3, U4 with the property that this sum is equal to 1? And the answer is yes, but not so easy. When we have just the representation of two states like this, we get states that looks like that, and these states actually they are called non-entangled states. We can check that not every 4 vectors will be coming from something like this. An example would be, if you think about this is a combination 4 complex numbers, and they have the property that this sum is equal to 0, but you can easily check that no combination of C1, C2, W1, W2 will produce this state. But when we have a quantum computer, there are you can create some interaction between these 2 qubits so that you generate every possible state that has this form, U1, U2, U3, U4, with this property. When you create a state that is not of this form, but it's a combination of 4 complex numbers, then we said that state is entangled. Some observations about this is that what we have done here with this distribution is what is called the tensor. It's a tensor product. Mathematically, it's called a tensor product. To summarize, we started with 2 qubits. Let's say this is labeled 0, this is labeled 1, this is labeled 0, and this is labeled 1. And we consider a state here. Let's say this is R1, and this is R2, with R1 squared plus R2 squared equal 1. And we consider a state here. Let's say this is R1 and this is R2 with R1 squared plus R2 squared equal 1. We notice that this state can be viewed as phi equal to C1 0 plus C2 1, and this one can be viewed, let's say, as C, and this is W1 0 plus W2 1, and there is a way to represent this state of this qubit being like this and this qubit being like that in this form, like U1 0 0 plus U2 0 1 plus U3 1 0 plus U4 1 1, and we pointed out that this is what is called the tensor product of these two vectors. Let's say tensor product, this is the symbol that is used, and these conditions are 1 squared plus R2 squared equal 1 and capital R1 squared plus capital R2 squared equal 1. They guaranteed that U1, the norm of U1 squared plus the norm of U4 squared is equal to 1. And the other thing that we pointed out is that a quantum computer has the property to achieve not only these states that are the tensor product of these two, but a quantum computer can do something physical to the system so that it generates a state that is called entangled. And let me just write that down. Entangled. An entangled state is a state that looks like U1 0 0 plus U4 1 1, but with the property that this state cannot be written like a state here, tensor product, a state there. And it has the property that norm of U1 squared plus norm of U4 squared equal 1. Actually, a quantum computer using entanglement gates, it can generate every possible combination U1, U2, U3, U4 with this property. And for that reason, we have that the possible states that can be reached using entanglement gates, and when you have a computer with two qubits, are states that looks like U1 0 0 plus U2 0 1 plus U3 1 0 plus U4 1 1, with the property that this sum is equal to 1, and then essentially we have points in C4 with this condition, and also we have the same issue that we have for 1 qubit, is that this state is considered to be the same as this state, e to the I theta 0 0 plus U2 e to the I theta 0 1 plus U3 e to the I theta 1 0 plus U4 e to the I theta 1 1. Then when we think about states, we have that the number of real parameters that we need to describe a system with 2 qubits is 6. Let's see why. Real parameters. When we think about C4, we need 8 real parameters, right? Every element here can be written like x1 plus y1i 0 0, and then plus x4 plus y4i 1 1. We need 8 parameters, but this condition here is just the condition like x1 squared plus x4 squared plus y1 squared plus y4 squared equal to 1. Actually, that provides that these states naturally lives in the 7-dimensional sphere. 7-dimensional sphere. But also we have this identification, and this identification reduces the number of parameters by 1. Then we end up with 6 parameters. 6 real parameters are needed to describe any 2-qubit system. Okay, I think this is it for this video.